By midday, a fresh fish pulled from the Nile could become dangerous. The air was hot, flies were everywhere, and there was no refrigerator waiting inside the house. Yet ancient Egyptians stored enough grain to feed towns, carried food across deserts, packed provisions onto riverboats, and placed preserved meat and fish inside tombs where traces survived for thousands of years. Their solution was not to keep every meal fresh in the modern sense. It was to change food before heat and microbes could destroy it. So how did ancient Egyptians preserve food without ice? And what could their methods actually accomplish? The first thing to understand is that ancient Egypt was not one place or one moment. Its history stretched across more than 3,000 years, from crowded delta settlements to villages in the dry south. Methods varied by period, region, household, season, and wealth. A temple estate storing grain for hundreds of workers faced a different problem from a family trying to save tomorrow's fish. Still, everyone confronted the same basic enemies. Moisture allowed mold and bacteria to grow. Warmth accelerated many forms of decay. Insects entered baskets and jars, rodents attacked grain, and exposed meat attracted flies. Ancient Egyptians could not see microorganisms, but generations of experience taught them which foods spoiled quickly and which treatments made them last. Their most important discovery was simple. Food did not always need to remain fresh to remain useful. Grain could be dried. Fish could be salted. Fruit could lose its moisture in the sun. Grapes could become wine, and cereal mixtures could become beer. Preservation often meant deliberately transforming the food into something more stable. But transformation was only part of the system. The Egyptians also controlled time. Highly perishable food was eaten soon after harvesting, catching, milking, or slaughtering whenever possible. Meals were prepared in manageable quantities, and leftovers were less valuable in a climate where cooked food could become unsafe quickly. The easiest way to preserve a fresh meal was sometimes not to store it at all. This explains why access mattered as much as technology. Communities beside the Nile could catch fish, gather vegetables, and obtain water repeatedly instead of storing every item for months. Local markets, estates, temples, and household networks kept food moving from producers to consumers. Preservation began with choosing which foods truly needed long storage and which could be replaced while still fresh. Fish presented the clearest challenge. The Nile and its connected waters provided many species, but a dead fish begins deteriorating rapidly. Removing moisture slowed that process. Fish could be opened, cleaned, exposed to dry air and sunlight, and sometimes combined with salt. The exact recipes differed, and surviving images do not give us a complete instruction manual, but physical evidence confirms that preserved fish was real. The British Museum holds a small ceramic bowl containing several sun-dried fish from Thebes. Museo Egizio in Turin preserves fish described as dried in salt from the New Kingdom tomb of Ka and Merit at Deir el-Medina. These are not merely painted scenes interpreted by modern viewers. They are surviving pieces of food that demonstrate the result of the process. Drying works because most organisms responsible for spoilage need available water. The sun supplies heat, while moving dry air carries moisture away. A thin or opened fish dries more evenly than a thick intact body. If the surface dries before the interior, however, moisture can remain trapped inside. So preparation and size would have mattered even if the Egyptians could not explain the microbiology. Salt added another defense. When enough salt surrounds food, it draws out water and creates conditions in which many microbes struggle to grow. Fish might be dried with salt or held in a salty environment. But we should avoid imagining one standardized Egyptian recipe. Archaeological objects prove that salted and dried products existed, while the precise salt concentration and storage life of most examples remain unknown. The result would not taste like a freshly caught fish. It would be firmer, saltier, and often require soaking or cooking before eating. That change was the point. A food that survived transport or storage was more valuable than a fresh food that rotted before reaching the table. Preservation exchanged texture and flavor for time. Meat posed an even greater problem. Large animals produced more food than one household could consume immediately, yet fresh cuts spoiled rapidly. Meat was also relatively expensive, and access varied sharply by status. Many ordinary Egyptians probably ate it less frequently than bread, vegetables, legumes, or fish, while temples and elite households had greater access to cattle and other animals. Evidence from burial context shows that Egyptians could prepare meat for extended preservation. The Metropolitan Museum of Art has a preserved shoulder of beef from the early New Kingdom, found in or near a specially shaped wooden food box in a Theban tomb. Other boxes from the same group were made with materials including wood, stucco, beeswax, and resin. That object is remarkable, but it needs careful interpretation. It was funerary equipment intended to nourish the dead, not an abandoned dinner from an ordinary kitchen. Burial treatment may have been more elaborate than everyday food storage. The surviving shoulder proves that meat could be deliberately preserved, but it does not prove that every household owned sealed meat boxes or followed the same procedure. Meat could also be dried or salted, and birds could be processed for storage. Removing internal organs, reducing moisture, and limiting contact with insects all slowed decay. Yet none of these methods made meat permanently safe. A badly dried center, damaged seal, or humid storeroom could turn an expensive supply into a dangerous loss. Fruit offered a friendlier challenge. Dates, figs, grapes, and dum palm fruit naturally contain sugar, and some could be dried to extend their useful life. Museo Egizio preserves a bowl of dried fruit from the tomb of Ka and Merit. Other finds combine seeds, dum nuts, and dried fish, showing how different durable foods could be stored together as provisions or offerings. Drying fruit concentrated its sweetness while reducing the water available for spoilage. The result was smaller and easier to transport, although not immune to insects or mold. Some fruits could also be processed into drinks, syrups, or cooked preparations. Once again, preservation created a new product rather than freezing the original fruit in time. Vegetables followed a mixed pattern. Onions and garlic could be stored more easily than tender greens because their bulbs were already suited to periods of dryness. Lentils, peas, and other pulses could last when fully dried. Fresh leaves, herbs, and watery vegetables were more likely to be seasonal, consumed quickly, or obtained repeatedly instead of being stored for long periods. The true foundation of Egyptian food security, however, was grain. Emmer wheat and barley could be harvested, threshed, winnowed, dried, and stored far longer than fresh animal products. Grain supplied the raw material for bread and beer, formed part of wages and rations, and could be collected by institutions. If kept sufficiently dry and protected from pests, it turned one harvest into food for the months ahead. Ancient Egyptian art repeatedly shows grain being measured, carried, and poured into storage structures. Archaeology confirms that large silos were not artistic inventions. At Tel Edfu, excavators uncovered a courtyard containing multiple circular mud brick silos that once served as a reserve for the town. Some were enormous, capable of holding many tons of wheat or barley. Those silos reveal that preservation was also an organizational problem. Grain had to be harvested at the right stage, dried before storage, moved by workers, measured by officials, and protected after it entered the building. A silo full of damp grain was not wealth. It was a future mass of mold, heat, insects, and wasted labor. Mud brick helped separate the grain from direct sunlight, while enclosed storage restricted access by animals and unauthorized people. Depictions and excavated structures suggest that grain could be poured into silos and later removed as needed. But no design eliminated every threat. Cracks admitted insects, roofs and walls needed repair, and rodents were persistent competitors. Small households used a different scale of the same idea. Pottery jars held dry goods such as grain, seeds, and fruit. Baskets provided light, inexpensive containers, although plant fibers were vulnerable to moisture and pests. Storerooms, platforms, lids, and careful placement helped separate food from dirty floors, animals, and daily household traffic. Sealing mattered because an open vessel invited insects, dust, and moisture. A New Kingdom storage jar from the tomb of Yuya and Jiu was closed with a pottery saucer tied into place with cloth. Its label indicates that it once held grain. The jar also used linen and mud, showing how ordinary materials could create a practical closure. A seal was not the same as modern vacuum packaging. It did not remove oxygen or sterilize the contents. Its value was more basic. It created a physical barrier and made interference visible. In institutional storage, sealings could also help control ownership and access, connecting food preservation with accounting and authority. Containers had to match their contents. Dry grain needed protection from moisture and pests. Oil required vessels that limited leakage. Wine and beer needed jars appropriate for fermentation, transport, and serving. The thousands of pottery fragments found at settlements are evidence of an entire food system built around moving and containing materials. Fermentation provided another form of controlled change. Ancient Egyptian bread and beer were closely connected to cereal processing, and archaeological models, equipment, residues, and production areas show that both were made on large scales. Microorganisms transformed sugars in ways people could observe and reproduce, even though they did not know what yeast was. Beer deserves special caution because it is surrounded by modern myths. It supplied calories and was distributed as part of rations, but it was not necessarily a drink that remained stable for months. Much Egyptian beer was probably produced for relatively prompt consumption. Fermentation changed the cereal mixture and created alcohol and acidity, yet the final product could still sour or spoil. The same warning applies to bread. Baking reduced moisture and killed many organisms present in the dough, but ordinary bread did not become permanent. It dried, hardened, attracted pests, or developed mold. Bakeries could produce large quantities repeatedly because a steady supply of grain was often more important than making each loaf survive for a long time. Wine was better suited to storage and transport when properly prepared and sealed. Jars could carry information about origin, production, or contents, particularly in elite and institutional settings. Alcohol, acidity, and a closed container improved durability, but ancient wine still changed with age and exposure. A damaged stopper could allow air and contaminants inside. Could Egyptians cool food with evaporating water? The physical principle certainly worked in Egypt's dry air. Water seeping through porous pottery can evaporate and cool the remaining contents. Egyptians used pottery extensively for water, and a shaded porous vessel could produce water cooler than the surrounding environment. However, popular claims sometimes go further and describe a complete ancient refrigerator identical to the modern pot-in-pot cooler. The archaeological evidence for that exact food cooling device in pharaonic households is not secure enough to treat it as universal fact. Modest evaporative cooling was possible, but drying, salting, fermentation, sealed storage, and rapid consumption are far better documented preservation strategies. Shade still mattered. A jar kept inside a thick-walled storeroom experienced less direct heating than one left in the sun. A cool part of a house could slow deterioration, even if it never approached the temperature of a refrigerator. During the night, desert air could become cooler, but the next day's heat would return. This meant food storage was always a race. Preservation slowed decay. It did not stop time. Households checked supplies, discarded damaged portions, reused leftovers quickly, and replaced fresh foods when possible. They may not have understood toxins or bacteria, but smell, color, texture, insects, and visible mold warned them when something had gone wrong. The risks were serious. Grain weevils could multiply inside stores. Rodents consumed food and contaminated what remained. Moisture entering a silo might trigger mold across a large section of grain. Salted fish prepared incorrectly could spoil beneath a dry-looking surface. A sealed jar protected its contents only until the seal failed. Preservation was also unequal. Wealthy estates and temples could maintain large storerooms, specialized workers, scribes, guards, and replacement supplies. A poor household had fewer containers and less food to lose, but the loss of one basket of grain could be devastating. The same technique produced different levels of security depending on who controlled the harvest. Institutional grain reserves supported more than meals. Grain could pay workers, provision expeditions, feed temple personnel, and help administrators manage shortages. Storage, therefore, became a form of power. Whoever controlled the silos controlled not only food but also labor, taxation, and the ability to endure a weak harvest. Yet even the largest granary depended on the Nile. If flooding, planting, or harvest failed, preservation could only stretch what already existed. It could not create grain from an empty field. Long-term survival required a chain of successful steps, from water management and farming to drying, transport, measurement, sealing, and distribution. Archaeological evidence also has an important bias. Tombs preserve food because they were sealed, protected, and located in exceptionally dry ground. Many tomb owners were wealthy enough to receive provisions that ordinary people could not afford. A preserved beef shoulder tells us what was technically possible, but household rubbish and settlement archaeology are essential for understanding what was common. Paintings introduce a different bias. Tomb scenes often show abundance, order, and ideal production. Workers move in rhythm, baskets overflow, and storerooms appear full. Real harvests were messy, grain spilled, pests entered, jars broke, officials made mistakes, and hungry people sometimes waited for rations that did not arrive. When we combine objects, settlement remains, artistic scenes, texts, and food residues, a consistent picture emerges. Ancient Egyptians did not possess one secret cooling machine. They created layers of protection. They selected naturally durable foods, removed moisture, added salt, fermented cereals and fruit, sealed containers, built storage structures, and organized consumption around the speed of decay. So how did ancient Egyptians keep food fresh without ice? Strictly speaking, much of it was not kept fresh. Fish became dried or salted fish. Grapes became wine or raisins. Grain waited in jars and silos until it became bread or beer. Perishable food was eaten quickly, while durable food was transformed, enclosed, counted, and guarded. That distinction is the real answer. Modern refrigeration tries to suspend change by lowering temperature. Egyptian preservation used change itself as a tool. Sunlight, dry air, salt, fermentation, pottery, mud brick, and disciplined storage turned fragile harvests into supplies that could outlast a season or survive a journey. The next time you see an ancient jar behind museum glass, imagine the problem it once solved. Inside could be a family's grain, a worker's ration, dried fish for a journey, or wine intended for a tomb. The container looks simple because the knowledge was carried by the people using it. They could not stop food from changing, but they learned how to make that change work in their favor. If you want more evidence-based stories about how ordinary people survived in ancient Egypt, subscribe and join the next journey.